Tell us about scholars London, and she will tell us about the theory versus models. So what can we test?
Okay, thank you very much for the invitation. Particularly, I would like to thank Luca for the invitation, the organization. And given the title of this conference, From Puzzles to New Insights in Fundamental Physics, I would like to address the question, theory versus models. What can we test? So as you know, the model that is accepted in cosmology is a phenomenological model, the lambda CDM model, which is based on one of the two robust theories that we have, GR. All the rest is phenomenological. In other words, dark matter, usually considered as cold dark matter. In addition, you have dark energy and inflation. So I would like to go one by one to these ingredients to see what is robust, what comes from observational kind of data, what we can test, what we can model. So the first ingredient, GR. It has passed all possible tests, classical tests, perihelion precession, velocity of light, gravitational exit, and as well the more modern test, strong gravity field, gravitational lensing, the FLRW cosmological solution, gravitational waves, sorry, I have to be here for that, and as well as from the Event Horizon Telescope, the test pictures of black holes. Now, how do we do the various tests that we have? The first one, so I'm going to use gravitational waves. So I'm going to tell you how we do the first class of test of the GR, which is what we call the consistency test. So if GR is the correct theory, then the waveform that you get from the data should match what your theory tells. And you have two sorts of tests, the residual test and the spiral merge lead down test. So the residual test tells you that if indeed GR is the correct theory, if I take my data, my waveform, and if I'm going to take out whatever GR tells me, what is going to remain? It should be just instrumental noise. And that's exactly what you find. For the case of inspiral merge down test, you say that if indeed GR is the correct theory, if I take the waveform only from the spiral, or I take as well the merger and the lead down, and I do a parameter estimation, the value that I get for the mass and speed should remain the same. Indeed, the test is correct. Then you go to a bit more complicated test, which is the parameterized test, and I will discuss later on about that. In other words, you try to have some kind of parameterization of effects beyond GR. And the difficult thing is once we are going to make this test, how can you do a kind of mapping from what you find to go back to your theory, to your model, let's put it more correctly, and see what implications it has. The first is the spiral test. In other words, what you are going to do is you are going to write your waveform in the frequency domain. You take the amplitude and the phase. This is valid for models where any deviation is more visible for the phase. You are going to write it in terms of post-Newtonian coefficients. You treat them independently, and then you have for each of them to deduce the parameter estimation, the value values for your parameters. The other is the rig-down test, which technically is more complicated, even though people work there. You want to construct parameterized rig-down waveforms, which are based on what you know from perturbative treatment of GR. Now, however, we know that we have the Penrose singularity theorem, and we know that in all these classical kind of models, at some point you are going to hit the singularity, and then you have to take quantum gravity corrections. I will go back to GR later. The second ingredient is dark matter. I put the C there with a different color because I tell you how we can test that. Now this is based on observational evidence, chronotation curves, gravitational lensing, hot gas flashes, cosmic microwave background radiation. So I insist, it's a phenomenological model. Now, as time goes on through years, they are different. The most probable candidates for what is going to be dark matter. For a long time, people considered the light a supersymmetric particle, LHC is not found supersymmetric. This model is a bit more abundant. So the most probable candidates now are primordial black holes and action-like particles, and I'll tell you how we search for that and how we put constraints. It has been also suggested modification of gravity. You have this kind of empirical mode, modified Newtonian dynamics, empirical law, quite cool, but once you try to embed it with more general theory, You're not going to have GR, you have what is called TELES, tensor vector scalar theory. But this theory, for the same value of its free parameters, cannot fit flat rotation curves and gravitational length out. So, dark energy. We have evidence from type 1 supernova, cosmic microwave background, baryon acoustic oscillations with gravitational length. There are as well some proposals here, if you want to consider cosmological constants, with the two problems that you have about fine-tuning coincidence. There is a number of modified matter model with tensors. You have a scalar field. K essence, you have nonlinear kinetic energy that's going to drive a kind of a negative pressure. Here you don't need to have any potential there. Coupled dark energy matter, for instance, the chameleon model, or you could have unified models of dark energy background. And of course, you have the zoom or modified gravity models, FFR models of gravity or density, degenerate, higher order scalar tensor theories, and so on. Models with extra dimension. And here already from the LBK data, there is a constraint that you can have once you have an electromagnetic counterpart and you want to make a kind of relation between the gravitational luminosity distance that you take from your interferometer and the electromagnetic one that you get from electromagnetic counterpart. And then we have inflation. Here I give you the three equivalent definitions of inflation. Inflation has been proposed in order to somehow cure the standard cosmological model from initial conditions. Its success, I believe, lies on the fact that you have adiabatic initial conditions. When you take perturbed Einstein's equation, you want to solve them, you have to say what initial conditions you have. Adiabatic or isochronous. Adiabatic, there is no fixation in the relative number of density species, and the CMB data, where you give the first peak at 220, this is a kind of some huge support for adiabatic initial conditions. But there is a myth if people say that the CMB data confirm inflation. They confirm the preference of adiabatic initial conditions, example, single field inflation, that's all. But there is a number of issues here. How generic is to start inflation? This has to be given from gravity. What is the equivalent field? Okay? Many models that have been proposed have kind of drawbacks from a particle physics point of view. We know of one scalar field, the Higgs, but you have to have a very large non-minimal coupling in order to fit the data. And of course, there is the Transplanckian problem. So, despite what people want to believe, despite, I don't know, thousands of papers, inflation remains a paradigm in search of a theory. And of course, you have various alternatives that have been proposed over the years: stringless cosmology, matter bounds, ekpyrotic scenario, or cyclic universe. So, in order to test a model if it is correct or not, of course, it has to be consistent by itself. Then it has to be motivated, and then it has to give some evidence. So the point is that raw data by themselves, they give not much information. You put them in a particular framework, so what you find at the end of the day is consistency of what you put at the beginning, and at the best case scenario, you just fit some free parameters. Here, already there is a problem with the H0 tensor, which is different kind of values that you get from late or early data measurements. So I would like to test models of gravity, dark matter candidates, and also inflation by using gravitational wave. So here you have a kind of cartoon of the various kinds of modified gravity models that exist in framework. And the difference that you are going to have regarding gravitational waves can be about generation. This is already a difficult problem in CR. Propagation, dispersion, birefringence, when you get the data from the source to the observer, then what is going to happen, you might have the right and left kind polarized mode to be exponentially suppressed or increased, therefore you have a parity violation, and then you might have as well amplitude data. And of course polarization. If you have beyond GR, you might have up to 6 polarization. And the Reynolds properties, there is a bit of a discussion on those before. So the first thing that you do, so I will give you some examples, I don't have time to discuss all of them. The dispersion relation. This is the genetic way that we can parameterize in a phenomenological way if you have beyond GR kind of models. So these are given for this parameter capital A and the small alpha. They take different values depending what is your preferred model that you would like to take. And then once you have the strain of the gravitational waves, the phase is going to be modified. As it goes from far away, this is going to build up, and then you can put constraints which you can map up to the particular model depending what are the massive gravity, parabolicity models, multi-factor space I mentioned, depending what values you want, and you can map what constraints there will be there. Now, parity violation. So the parity violation we studied by considering the gravitational wave background. This is the counterpart of the electromagnetic background. So if there is of cosmological origin, from phase transitions, from effects, from whatever you want at the beginning of the universe, on the top of that, you have gravitational waves from sources, compact binaries, which are far away, and therefore they are weak, you cannot identify them, and they build the gravitational wave background. Given that historical people thought at the beginning that all that is cosmological origin, then it's given through a dimensionless parameter of all kinds that we have in cosmology, the omega W, the energy density of gravitational waves in a logarithmic interval of frequency and normalized by the critical energy density. So this is the gravitational wave background, okay? So what we do is because the signal that you get is much bigger than the noise, the only way that you can disentangle it, if you take the correlation of the output of two detectors, I and J, okay, I'm in Fourier space, it is my frequency. Now, the correlation between the strain and the noise is zero, so you might have a correlation of noise of your detectors, we know how to take it into account. So this is the object that we want to calculate. If you have parity violation, then you have left and right kind of components, which are going to be given in terms of the Stokes parameters, I and P. So the omega GW has a contribution which comes from the parity violation. Okay, these quantities here, forget it, they have to do with the orientation and the separation between your interferometers. So we looked in the data for parity violation. So far, over the 3 runs of the Library-Cocagra collaboration, there is no evidence for any parity violation. Now, polarization. Okay, you might have up to 6 polarizations. If you want from your transits to find polarization, it's very difficult because you need 6 detectors, we have 3. 2 of them have the same orientation, we cannot do it. But we did, again, a Bayesian study by using the gravitational background, okay, where we are going to get a contribution from tensor vector scalar laws. These are 3 parameters, the omega 0 t or d or s, and this kind of power laws. So we did a Bayesian kind of approach by giving the same priors for the signal versus the noise, the same prior for the GR versus non-GR. In other words, if I had only tensorial modes or the extra ones. And this is an approach that is used from that time with the collaboration. There is no evidence for any kind of polarization in the data. The Riemann properties. So there are 2 different kinds that you have. The Riemann, so if you consider that GR is a correct theory, you have the Noether conjecture. In other words, you have 2 black holes which are going to merge. You are going to get a perturbed Kerr black hole that is going to arrive at its stationary state by emitting gravitational waves in a particular quasi-normal mode, which depend only on the mass and the speed. The LDK data are in agreement with Kerr arrangements. There was the suggestion about echoes, okay? So there might be theories that they lead to the existence of these exotic objects, which are more massive than neutron stars, but without horizon. So as the signal comes to you, it's going to interact with the object. Some of the signal is going to be trapped, and what is going to arrive to the observer is a kind of series of echoes, and as they come to you, their amplitude and their frequency is going to decrease. Their absence at 90% of any kind of such exotic object. Now, I discussed about dark matter. How can we, somebody asked a question the other day, how you can test dark matter with gravitational waves. So what I'm going to tell you is that with 3G detectors, we'll be able to study the event of mergers of binary objects depending on what is the microstructure of your dark matter. So if you consider supergalactic scales, then astrophysicists tell us that your data are consistent with cold dark matter and no interactions. However, it has been pointed out that if you are at larger exits, what is more important to take is to go to take small scales, subgalactic kind of scales. And then the structure formation is going to depend on what is the microstructure of dark matter. So you can consider warm, interactive, or fuzzy dark matter. Any of the three of them is going generically to give you suppression at large scales. So if you go to calculate what is going to be the merger rate, depending what is the origin of the dark matter, you will see that as you go to a redshift which is bigger than about 5, you cannot see it, but any of non-cold dark matter gives you this one, which is going to be within the detectability of fluid detectors. Now, the other thing is about the two candidates that I said that they are most probable. Axion, pseudoscalar particles, or primordial black holes. So if you take, so what we have studied is the case of an axion which couples to the neutral matter in the same way like the QCD axion, but has lighter mass. So if you find such a situation without a very dense object, like a neutron star, then the potential of the axion is going to take this extra kind of term of the correction. Okay? So you are going to have a phase transition that will bring your field from a zero to a non-zero value. So what's happening is that if you have two neutron stars with this kind of axion phase, there's going to be a force, attractive or repulsive, depending on what is the axion charge. So if they are going to collide, you are going to have axial radiation that will come in. So some years back, we did an AFT approach and we found the first post-Newtonian kind of corrections in the orbital dynamics, the radiative power, and the gravitational wave from mergers of binary neutron stars with such an axial fit. And at the time, there was no data. We said LIGO will be able to exclude axions with this mass and this kind of decay constant. And then, a few years later, we have the GW17 or 817. We did a kind of post-Newtonian approach. These are the first kind of Lydic term corrections that you have in the phase from the axial field. These are post-Newtonian corrections. And then we were able, by the deep phasing kind of data, to put constraint on masses below 10 to the minus 11 eV, and within this kind of decay constant range. This data will increase by square root of n, if n is the number of such other binary neutron star data that we might have. Then there is a huge kind of variety of models that can lead to primordial black holes. So it's a candidate that people consider it often. Now, primordial black holes gain a lot of interest because they can span a big large of mass, and they can provide an origin for the dark matter, which usually you constrain this parameter f, which is the contribution of primordial black holes to the dark matter in the universe. Okay? Now, the black holes that they gain a lot of interest are between 10 and 100 solar masses because of the LDK kind of data. So then what people ask the question, could be any of the LDK CBC data we have be of primordial black holes and not of astrophysical black holes? So how people have studied this question? They went to compare the observed gravitational wave length rates with what is predicted by a population of primordial black holes. And there is no agreement in the literature. It depends if you have late of early binary formation. But in all these studies, the black holes, the primordial black holes, have been considered like constant Schwarzschild masses. And this goes back from the time of Hawking, who can put down that this is incorrect, because they are formed at very early times, and we cannot neglect the fact that they are in an expanding universe. So what is the correct metric? This is a question that I don't have the answer. If any of relativists could help in finding this question, that would be great. So I don't know what is the correct answer
to treat the primordial black holes. Certainly, it's not to consider them as a constant sorting mass. So, as an example, I don't claim that this is the metric to use. We consider this Takuta metric. Why? Because it seems to be less pathological than other methods, and because at large distances it gives the FLRW metric universe. So what you find with this metric is you find that you have stricter conditions for the formation of binary black hole. You have two constraints that you have to fulfill. The Newtonian force must dominate over cosmological force, so they can create a binary, and the orbital decay, because they emit gravitational waves, must dominate over the expansion of the universe that puts them through. If you take that into account, you see that such black holes have coalesced much before you have the data of their decay. So you can, like that, eliminate the LIGO bounds on primordial black holes. Of course, it would be great if we were able to find a subsolar mass, because that would be a primordial black hole. Now, and everybody looks for that. So a couple of years ago, we considered a kind of candidate from the LIGO catalogs, which from the collaboration is not put forward as a confident candidate because the false alarm ratio is too low to be claimed like a real kind of thing. Anyway, we said, let us consider that. And then we had a larger range of frequencies. We considered the waveforms where we take the mass, the spin, the eccentricity. We remove any glitches that were there. And when we did the parameter estimation, we found that the secondary component has a mass which is smaller than one solar mass at 80% confidence level, which is quite light to be a neutron star. That most probably tell us that should be a black hole of the primordial or exotic origin. The primary mass is in what we call the lower mass gap of the data. And then we did a test, which is this CBC origin hypothesis. In other words, is it a real CBC, compact binary collision, or it could be a kind of noise. So we did the signal coherence test, and the bias we found supports more that is a real CBC candidate. So I'm not saying that this is a primordial black hole. I'm saying that it could be, okay? Then, of course, you can go to see in the gravitational wave background, and you put constraint in the primordial black holes. So we consider, because usually people take primordial black holes monochromatic, they have the same mass. We took this kind either monochromatic or a log normal Gaussian distribution, and we considered early and late binaries of primordial black holes. The binaries are formed soon after the formation of the black holes in the radiation dominated or much later. If they are much later, then you have more kind of mergers that they can form. And we put these are the three constraints. In a few months, you can see out the 4 data that they will come, and we'll have updated all the constraints that we put here. Constraints in the contribution of primordial black holes in the dark matter of the universe from radiation wave data. Now, then I would like, I have still time, no? Oh, fine. So then I would like to go to this dark energy thing. There are all this arena of zoo of models, okay, that are completely phenomenological, and they can try to explain the late time exponential expansion of the universe. So what's happening here? Take for instance a Hordensi or the DH host or string theory models or whatever you want. Then in many of them you have that you break an origin pattern. But if you want to be complete your theory, then at some higher energy scales, you could have a luminal velocity for the propagation of gravitational waves. Now we have a data. We have that within the LIGO range, frequency range, we have a constraint of what is the deviation of the propagation of gravitational waves between the speed of light. But it could be that you have this arena of models where the propagation depends on the frequency. Okay? So, can we put constraints? So we took two ansatz models for what will be in order to model the frequency dependence of propagation of gravitational waves, And we saw, I have no time to go into details, but because then it's Newtonian expansion, was quite heavy, but what we found is that LISA will be able to put constraints in such models where there is a propagation of gravitons which depends on the frequency. Then, of course, the difficult task is to see how you can map these constraints in the theory which is behind. Now, and then it comes the whole idea of inflation. And for me, inflation is not through the scalar field, it's through gravitational corrections. So the whole idea, and I would like here I make this point, you find many studies in the literature where they take a modified Friedman dynamics, and then you say it comes from a quantum gravity-inspired model, and I put by hand a scalar field, and I see how inflation changes. You can do that, it's a nice exercise, but doesn't give you any kind of insight, okay? So then the question is, I believe that this quantum gravity should come from, that this early accelerated expansion should come from a quantum gravity kind of effect. An example, some years back we saw that in the context of a group quantum cosmology, which is based on the idea of the quantum space as a context matrix system. Your theory is built by choosing a complex scalar field sigma and the axiom, which is given by this kinetic term, and then by this interaction kind of polynomials that you given here. So you have this kind of quantity of your geometry, the values of this parameter, it tells you how you glue them together. And even in the absence of a scalar field, this is the volume. So this is the condition that even in the absence of background can tell you what is the condition that you have to fulfill in order for exponential expansion to take place. And what we have found is that depending on how you group these things together, indeed, you might have an exponential expansion at the stage of the universe. I'm not saying that this is the answer, I'm saying that this is one example of how quantum gravity proposals could lead to an area of exponential expansion. And this is a model that can be also tested with gravitational waves if you had electromagnetic counterclocks. Because what you can do is, let's say you consider that your space-time is distorted by some kind of quantum gravity effects, which are captured in this space-time measure rho, and this kinetic term k, and my j is just the source term. So I can go to study tensor perturbations, and you can see that the amplitude of gravitational waves will depend on this quantity here, which is dimensionless, and this kind of power law distance behavior where gamma has a particular value depending what is the quantum gravity proposal we have assumed. So by using simulated data for the sensitivity of LISA and for exit of a bit more than 3, we have found that group field theory, spin forms, or loop quantum gravity could be tested by gravitational waves accompanied by electromagnetic counterclocks. I'm not saying these are the correct ones, I'm saying these are models that could be tested. So here I arrive at my discussion remarks final thing. Observational data studied within the framework of a particular theoretical model. So I think it's a myth if people go around saying the CMB data confirm the lambda CDA model. No, it's the other way around. The lambda CDA model was put to fit the data. So what you do at the best case is a consistency check. And therefore, if you want to be sure that something is there, you take a particularly different framework and you analyze your data. Second, a given theoretical framework may not be valid for any case that you study. And here again is the example of the concordance, cosmological model, and the issue of tension. Quantum gravity is important in describing the early universe. So, I don't think that it's useful to continue the exercise that goes along for many years, so people take modified Friedman equation and put it by hand a scalar field and say, well, that's how equations don't work. So that's a nice exercise, but that's all. Now, of course, one is tempted to take the data and study beyond real models, but one is to be sure when you want to study, for instance, how will be the gravitational waves that I take of the merger of two black holes in a very exotic theory, first of all, you have to find that there are black hole solutions, therefore that they are stable. Third, to go to calculate what is going to be the signal that you might have before you run into conclusions. That's why I believe that all these, let's say, gravity-motivated models can be used in order to test qualitatively and not quantitative kind of implications of the theory. And with that, thank you very much.
We have time for some questions.
Thanks for the talk. Just one small question about the Lorentz and bias violations that you mentioned by Lisa. Could you?
I didn't mention by Lisa. I mentioned that Lisa will be able to put constraints not only to the GR parameters, but as well in the way that you model the dependence on the frequency of CT. That's what I said for Lisa. I cannot do it without Lisa. I cannot do it now.
I just wanted to. Can you put it in context with respect to the constraints that come, for example, from cosmic fluxes, cosmic rays, and so forth? Is it in the context of those? Because, for example, there are some. I remember some papers on Lorentz and bias violations that constraints on Lorentz and bias violations coming from cosmic rays, and I don't know anything.
I don't think that they will talk that they should be in the same frequency range. These kind of differences. I think that's the big difference.
Okay, thank you.
Hi, thank you so much for the talk, very clear. I do have a question about the residual studies that you do. When
About what?
The residual studies when you compare against like the background data. I wonder if it's needed to, if you do this research, we kind of need to know the background gravitational waves, like something about the background, or if we can just like,
you model the background. I mean, you know, you have a data, a bank of waveforms, which depends on the parameters, which would be mass, spin, eccentricity, whatever. So you map it with that, and you want to find what is the best fit. You extract that. What remains, it should be just noise.
Yeah, so we don't have to understand a lot about what the background is or where it's coming from.
What do you mean by the background? The background is the hypothesis. You have an astrophysical source there. So the background, you know what it is. It should be binary black holes or black hole and neutron star. You have to model that. Otherwise, you don't have the waveform at all. So in order to, so the waveform depends on what is the origin, not the parameters of the object, but the origin of the object.
I see. And
I mean,
everything
if you
else-
have, I don't know, cosmic strings that is completely different in the waveform.
Right, like just everything that is not there, you just assume it's some noise.
I mean, it should be noise. It should be instrumental noise if GR is correct.
Sure.
If I find the best fit waveform, and that I subtract it from the waveform that my data give me, what remains should be instrumental noise. If it's not, then it's beyond GR fingerprint.
Right, and there are like ways to estimate this instrumental noise, like it's a function.
Yeah, instrumental noise, you can, no, you know instrumental noise because you need the instrumental noise every time you want to see what measure if it's you know, so the instrumental noise, you know.
Okay, thank you.
There are some models for the noise. If you have the background noise of two detectors for the stochastic, we have that is a bit more complicated, but yes, different models.
Thank you.
Next, is there question about the phone?
Yeah, you mentioned the importance of having adiabatic perturbations.
Yes.
What are the bounds on isocurvature fluctuation?
The isochemical perturbation is completely out unless you have what is called
What does completely mean?
I mean that if you have the position of the peak is shifted to higher L, which means it's smaller angular separation.
What is the bound?
Sorry?
What is the bound?
It goes to about an L of 350 or 400. Now you can see to what
How much would it change?
from 220, 300, 400. You have the peak, you know? My data give me where the peak is. The peak.
Could the isocurvature fluctuations be 1,000 of the adiabatic fluctuation? 1 million? What's the
It depends. It depends on the model. Isocurvature perturbation you can have, for instance, from topological defects. If you take on extremes, you have domain walls, they will give you a peak which is fat and low. It's not going to be a delta function. So it is off by, I don't know, 70%, at least. It's completely off. Now there are models where they try from isocurvature to go to adiabatic. This is yet another kind of episode. But my point is that the data prefer adiabatic initial conditions. Inflation is an example. Single digit inflation is an example.
Yes, that's fine. I'm just
Yeah.
wondering how much isocurvature is excluded.
At least at 70%.
Okay, but that sounds very impressive. I mean, many, you could imagine 500 million, 1,000 from different microphysical sources.
More questions?
I guess what I'm saying is it should be looked for system. I guess what I'm saying is that it should be looked for systematically because many microphysical pictures.
I agree with you, and we have pointed out how a combination of two could work, but the biggest part of the community presents that as a proof of inflation.
One last question, and then we put the discussion where in case you can do last question.
So you mentioned that the data so far from the backgrounds rules out the extra polarizations. I'm curious to know at what significance, and so what does that tell us about in terms of are we just ruling out anything that has extra
I'm
polarizations?
saying that up to now, at the confidence level of, I don't know, 80 at least percent, I have the numbers, I don't remember the rest of my life, it has a full agreement with GR. That's all. Now, I mean, the more data you have, the more kind of constraint. Up to now, there cannot be any evidence, any support for something beyond GR.
Okay, so around 80%, is that the?
At least.
Okay.
At least.
Okay.
This is the data from the background, from transients effects. Unfortunately, the number of interferometers we have and their orientation does not help for doing extra polarization.
Okay, as we are running out of time, and it's time to begin.
Okay.